Okay, good afternoon. In today's session, I will be discussing about the torsion of circular shafts. Torsion of circular shafts. Torsion or torque means the twisting moment. Torsion means the twisting moment. So, which we generally come across in shafts. Okay, so this moment helps rotating of shafts and hence the transfer of power transmission through rotation of shafts. Okay, and the rotation is caused by the twisting moment, okay, or torque, sometimes also called as torsion. Okay, so generally we'll see these shafts in workshops and factories, okay, in which the shafts are adopted for transmission of energy. Okay, so the turning force is applied to transmit energy by rotation, and this force is applied either to the rim of a pulley keyed to the shaft or at any other suitable point. Okay, and the product of this turning force and the distance of the point from the axis of the shaft. This is axis of the shaft. Okay, the shaft like this. The twisting force is applied, which causes a twisting moment. We represent that by T. Okay, so here the twisting moment is equal to force into the distance R from the axis. Okay, this product of force, twisting force, turning force multiplied by the distance from the axis is said to be the torque or twisting moment. Okay, and the shaft is said to be subjected to torsion. And what happens is, due to torsion, each and every cross section, because this cross section is twisted, and every other cross section also gets twisted, causing shear stresses across the cross sections. Okay, every cross section is subjected to shear stress due to torsion. Each and every cross section of the shaft is subjected to torsion. Twisting moment is subjected to shear stresses also. So we derive here the torsion equation. Just like bending equation, here we derive torsion equation. Okay, and we make some assumptions in this derivation of torsion equation. Okay, so the assumptions made in the derivation of torsion equation are: the first assumption is the material of the shaft is uniform throughout, okay, homogeneous, and the twist along the shaft is uniform. The twist is uniform along the shaft, and the normal cross sections of the shaft, which were plane and circular before twist is applied, remains straight, remains plane and circular after twist also. Okay, and the fourth assumption is all diameters of the normal cross section which were straight before twist remain straight after twist. Okay, so with these assumptions we will proceed to derive the torsion equation. Okay, and here this is applicable only when the torque applied is small and the angle of twist is also small and within the limits. Okay, when the torsion is within the limits, then only this equation is applicable. Now consider a circular shaft which is fixed at one end and subjected to a twisting moment at the other end. Twisting moment T. So you consider a line CA before applying the torque. The line CA is parallel to the axis of the shaft. Okay, the length of shaft is L. Okay, now after twist is applied, the cross section undergoes deformation or distortion here. This point A moves to A dash, moves to A dash. That means the cross section is subjected to twist, and O is the center of this circular cross section. The angle AO A dash is called the angle of twist. Angle of twist, theta. Here we are representing it by theta. And this angle phi is nothing but shear strain. Actually, shear strain is by definition it is equal to the lateral displacement, lateral deformation or distortion A dash per unit length. Per unit length. That is, shear strain is the ratio of A dash to L, which is nothing but tan phi. Tan phi, and for all practical cases, this angle of twist is very small, and this tan phi can be taken equal to approximately angle phi only. Okay, because phi is very small. Phi is very small. Tan phi can be taken as phi. Okay, so here the radius of shaft is capital R and length of shaft L. T is the torque or twisting moment in Newton millimeters. So, yeah. Initially, the line CA, which is parallel to the axis of the shaft, is deformed to a new position CA dash, and OA is deformed to OA dash. Okay, OA is deformed to OA dash. The new position of OA after being twisted is OA dash, and this angle is theta, the angle of twist. Okay, angle of twist. Okay, angle ACA is phi and angle AOA is theta, AOA dash. and tau is the shear stress induced at the surface. That is the maximum shear stress. Now C is shear modulus or modulus of rigidity. Okay, and now the shear strain is deformation per unit length, lateral deformation per unit length, that is A dash by L, which is equal to tan phi, and that is equal to phi since phi is very small. Since phi is very small. Okay, and also from this figure, O being the center, the length of arc A dash is equal to radius is r and angle made by the arc is theta. So r theta in radians is equal to the length of arc A dash. So replacing in this A dash by r theta, you will have phi equal to r theta by L, and also by definition of shear modulus, which is the ratio of shear stress to shear strain, that is tau by phi, from which you will get the shear strain phi as tau by C. Okay, so equating these two from 1 and 2, you will have tau by C equal to r theta by L, or tau by r equal to C theta by L. So this is one relation, and this also can be equated to Q by R. Okay, where Q is the shear stress at any radial distance R. From center, if you consider radial distance small r, capital R is the radius of shaft, and at any radial distance r, the shear stress is Q. Okay, so here the shear stress varies with the distance from the axis. Shear stress varies from the axis to the outer periphery of the shaft, increases actually. Okay, that means the shear stress depends on the distance from the axis of the shaft, and it will be maximum at the outer surface, and which is represented by tau. At a radial distance of r, tau is the shear stress, that is the maximum shear stress to which the shaft is subjected to. Okay, this is one relation in torsion equation, one part of torsion equation. Okay, and there is one more relation that we will see here. So now, considering the strength of the solid shaft, we consider here with radius r and tau shear stress. Okay, yeah, mainly here the power is transmitted through shafts. Okay, through shafts, the power is transmitted. So now, to derive the other part of this equation, let us consider the cross section of the shaft with radius r, and consider a small element at a radial distance r, x here, at a radial distance x, and thickness dx. Okay, you consider small elemental ring with area dA. at a distance x and thickness being dx. So the area of this ring, elementary area, is given by 2 pi x, that is the length, multiplied by thickness. Okay, length multiplied by thickness dx. So length means length of this ring is nothing but circumference, isn't it? This length is nothing but 2 pi x. 2 pi x is the length of this ring, elemental ring, multiplied by thickness gives elemental area dA. Okay, and the shear stress at this section is tau x. At a distance x, the shear stress is represented as tau x, which is given by tau into x by r. Tau into x by r, because from the previous relation we have seen tau by r equal to q by small r. Here q is shear stress at any distance x, at any radial distance r actually. Okay, in this one we are taking q as tau x and r as x. Okay, so from this relation we will have tau x equal to tau by r into x. Tau by r into x. This is small x, distance from center of the shaft. Okay, so you have this relation for shear stress at any radial distance x. Now the turning force acting on the element is represented by dF, which is shear stress multiplied by area. Shear stress at distance x is tau x and area of the elemental ring is dA. Okay, so this force will be acting all around the circumference. Okay, the force will be acting all around the circumference dA. Okay, so the torque or twisting moment caused by this force is equal to dF into x. The torque or twisting moment is equal to dF into x. So what is dF? Let us see first. The force dF is shear stress tau x multiplied by area. Tau x is tau by r into x and area dA, 2 pi x dx. Okay, so 2 pi tau by r into x square dx, x into x square dx. Okay, so this is the force on the elemental ring. Now how will you get the total force? Total force acting on the shaft, turning force acting on the shaft. So this is the force acting on one of the elemental rings at a radial distance x. You will have so many such elemental rings. So by summing up the turning forces acting on all these elemental rings, you will get the total force F. And the summing up is obtained by integration. Okay, so F is obtained by integrating dF between the limits 0 to r. 0 to r. R is the radius of shaft. Okay, so integral dF is equal to the total turning force. Yeah. Okay, so the turning force is equal to this one, and turning moment is, what is turning moment? Torque, turning force multiplied by distance. Turning force multiplied by distance. So that is 2 pi tau. This is the turning force multiplied by distance. That is the turning moment or twisting moment. Okay. This is the turning moment on elemental ring. One of the elemental rings at a distance x. How will you get the total turning moment, twisting moment? By integrating this between the limits 0 to r. Okay. By integrating between the limits 0 to r, you will get the total turning moment. Okay. So integral of 2 pi tau by r into x cube by x cube dx between the limits 0 to r. Okay. Now, what will be the integral of this? Let us see. So 2 pi tau by r, these are constants. Okay. This is constant. Taking that out, you will have x power 4 by 4 integral of this. Between the limits 0 to r gives r power 4 by 4. So finally you will get the torque as pi t by pi tau by 2 into r cube. Okay, or pi tau by 16 into d cube, replacing r by d by 2, where d is the diameter of the shaft. So this, by rearranging, you will have pi d cube by 16 into tau. So this is the total twisting moment, total torque acting on the shaft. Okay, total torque on the shaft is pi d cube by 16 into tau. Pi d cube by 16 into tau. Now we know the polar modulus or polar moment of inertia I suffix p or j. For a circular section, the polar moment of inertia is ix plus iy. That is pi d power 4 by 64 plus pi d power 4 by 64. That is polar moment of inertia. Pi d power 4 by 32. Okay. And polar section modulus. Polar section modulus is I by r. Ip by r. Polar modulus is Ip by radial distance. Okay, that is pi d power 4 by 32 divided by d by 2. So which you will get pi d cube by 16. So this pi d cube by 16 is nothing but the polar modulus, which is Ip by r, or simply j by r. J is polar moment of inertia. So you can replace this pi d cube by 16 by j by r into tau. J by r into tau. So from which you will get, this is another relation actually. This is another relation. Twisting moment is equal to j by r into tau, or t by j is equal to tau by r. Already we have one relation for tau by r, which is equal to c theta by l. The previous relation what we have derived is tau by r equal to c theta by l, and this relation tau by j equal to tau by t by j equal to tau by r. This is another relation. So by combining these two, you will have tau by j, t by j equal to tau by r equal to c theta by l. Okay, this is the equation, torsion equation. Okay, just like bending equation, we have this torsion equation. Okay, you know what is bending equation? We have seen, I think, in one of the previous sessions. We have discussed m by I is equal to f by y equal to e by r. Okay, this resembles bending equation. Torsion equation resembles bending equation. Here m is bending moment, t is twisting moment, I is moment of inertia about one of the axes, ix. Okay, and j is polar moment of inertia. Tau is shear stress and f is bending stress, and y is radial distance. Here r is the radial distance. E is Young's modulus, C is rigidity modulus. Okay, and R is the radius of elastic curve, and here L is the length of the shaft. Okay, so this is the relation which is the governing equation actually in case of circular shafts. Okay, that is all for today's session. Thank you. We'll discuss some other topic in the next session.
Like, share and subscribe. Hit the bell icon for more updates.